Okay, good morning, everybody. So I'm Roland Trautner from ESA. In my real life, I sort of work on management of development of space instrumentation for exploration missions. And basically today I'm talk a bit about permittivity sensors. I'm doing that on behalf of several colleagues, not only in ESA, but also in academia and industry, notably Technical University of Munich, who are our main partner on two of the flight projects that we have at the moment, and also colleagues at MBRSC, that's the Mohammed bin Rashid Space Center in the Emirates, who are building their little lunar rovers. So I'm going to basically introduce the measurement principle, talk a bit about the science that we can do on the moon with this type of sensors, introduce a bit the heritage that we have at ESA with this type of instrumentation, about the measurement capabilities, and then I introduce two of the flight projects that we have for which we are developing that type of sensors. In its most complex shape, and also the sort of configuration that is most accurate in terms of the measurement quality, permittivity sensors come as quadrupolar probes. In such a configuration, we basically use two electrodes to inject the current into a medium, and we use two additional electrodes to measure the potential in the medium. We do that first in vacuum and then in the medium of interest. And we can do that across a certain range of frequencies. And then by basically using these relatively simple relationships here on the left, you can derive the conductivity and the relative permittivity of the medium. And that works in a very large range of conductivities and the electric constants of the medium. Now, in certain environments, we can actually go for a simplified configuration. If the conductivity of the medium is very low, then the impedance between the electrode and the medium is less important, and we can actually do a simplified measurement using only two electrodes. In such a configuration, then we basically apply a voltage between our two electrodes. We measure the current that flows into the medium. We do that in vacuum. We do that in the medium across the frequency range of interest. And that basically gives us the electric constant of the medium. When I say two electrodes, actually that can, in principle, on many types of vehicles, can be only one electrode, because we can use the chassis of the vehicle as the second electrode. And because, as you can imagine, that can lead to actually very low mass and very complexity types of instrumentation. And that's one of the main reasons why this type of sensor is attractive. So basically on the moon, we can measure the dielectric constant of the regolith and of embedded materials. The dielectric constant has a well-known relationship with the density of materials. So by measuring the dielectric constant, we can infer the density, which can be helpful for example, pairing this type of sensor with investigations of samples. Then the dielectric constant is, of course, because it is related to the density, we can quite easily distinguish relatively loose regolith, so lunar soil, from embedded objects like pebbles, like rocks and so on, which have a much higher density and therefore also a much higher dielectric constant. In addition, we can look at the dielectric constant over frequency. And one of the very interesting materials or resources on the moon, water, has a very specific signature across the frequency range. By doing a measurement across a frequency range of interest, and also by doing an accompanying temperature measurement, we can basically derive the water ice content of the regolith by doing this type of measurements. In terms of heritage, ESA has flown multiple instantiations of permittivity probes on previous missions. We had one on Huygens. We had also one on the Rosetta lander. Both of them went into environments where we knew very little about what we would find, and therefore quadrupolar probes were the perfect configuration for this type of measurements. Now, we have then also done some prototyping for subsurface instrumentation, like the mole prototype that you can see here in the middle. That was done in the early 2000s, and that actually led to the type of instrumentation that we are flying today. We have one development ongoing for Prospect, which is going to fly in CP22. There have been a few talks on Prospect in the last few days, and you can find more information there. And the latest incarnation is a sensor on a rover, basically, on the Rashid 3 rover from MBRSC, where we have an electrode or multiple electrodes on the wheels and doing measurements basically as the rover is moving across the surface. In terms of measurement performance, all the implementations that we had so far had an accuracy of better than 10% across the full temperature range, also across the range of materials and material properties that these probes were designed for. Actually, in most parts of the measurement range, the accuracy is much better. On Huygens, for example, we have demonstrated an accuracy of about ±2% over most of the measurement range. On the Rosetta lander, the actual accuracy achieved in flight, as published, is in the ballpark of ±8%. Noting that the Rosetta lander didn't land exactly nominally, but basically was sort of hanging in a ditch with its feet partially in the vacuum. And then the Prospect P sensor is relatively similar. This table is from a paper on the Prospect P sensor that we have published a while ago. And the Prospect sensor basically achieves an accuracy also close to that, ±12 to 13%. So on Prospect, as you may have seen during the talks in the last few days, we have a big drill with a maximum drilling depth of 1 meter. And as part of the drill rod here, we have a permittivity sensor about 40 centimeters from the drill tip. Obviously, the ideal position would be right at the drill tip, but that space on Prospect is occupied by the sampling mechanisms. Therefore, we had to move it a little bit further back. And basically, since we are 40 centimeters from the drill tip and we can drill up to 1 meter deep, we can basically do permittivity measurements from the surface down to about 60 centimeters. The resource requirements of this sensor are very modest. We have a single electrode with a diameter of about 1 centimeter. The mass of the whole sensor, including the front-end electronics, is in the ballpark of 50 grams, and power consumption is in the ballpark of less than 300 milliwatts. Measurement durations are depending on the situation between a few seconds and a few minutes. Since we can also infer the density of the material from the permittivity measurements, we are basically also supporting the PROSPER measurements. As you may have heard, PROSPER is basically processing a sample that has been acquired by the drill. PROSPER is measuring so PROSPER cannot measure the mass, but the volume is defined. So by knowing the volume and doing a density, basically inferring the density from permittivity measurements, we can derive the mass of the sample with a certain error bar. Then what we can also do on this sensor is, because we can measure the distance between the electrode and the borehole wall, we can basically give the drill operator some information about how the drill is sitting in the borehole, whether there's a risk of jamming and so on. So we can contribute to situational awareness. And of course, we can detect subsurface structures like rocks, pebbles, and so on that we measure when we go deeper in the borehole. So the measurement accuracy of this sensor is in the ballpark of ±12 to 13%. That takes into account multiple measurements along the azimuth. So basically, we are rotating the drill, doing a measurement, rotating another few degrees, doing a measurement, and can do a measurement all around. If we have enough time and bandwidth, we can actually do subsurface imaging by basically doing multiple of these azimuth measurements every maybe 2 or every few centimeters down in depth. And then we have a sort of electrical image of the borehole wall. We can detect ice with an accuracy or with a detection limit of about 1% in mass with our 1 centimeter electrode and a measurement frequency of 1.5 hertz. And 1.5 hertz means 1.5 hertz upwards. We excite the electrodes with a square wave. So that means that we have 1.5 hertz, 4.5 hertz, and then the multiples of this frequency up to about 100 hertz. When we increase the temperature of the regolith, then the water signature improves. So we get more sensitive. So what we can do in the situation of Prospect is that we can heat up the drill rod. That can then heat up the regolith in the vicinity of the drill rod. And by doing these measurements, basically, we can even increase our sensitivity for water ice detection. And we have temperature sensors in the drill rod, one in the tip and a few more along the mechanisms. Then the latest incarnation of flight sensor that we're working on is for the Rashid 3 rover with our partners in the Emirates and MBRSC. MBRSC have basically developed a small rover that they have already launched in 2022. Unfortunately, their landing was not successful. So they are now basically working on a bigger rover called Rashid 3. And they have approached ESA for instrumentation for that rover. And we have proposed a few candidate payloads, and they have selected the permittivity sensor also mainly because of the low mass and power requirements. So at the moment, Technical University of Munich is doing a feasibility study and prototyping for all the elements of our sensor. An MOU between ESA and the Emirates is under finalization, and we already had a first payload team meeting 2 weeks ago, which was very useful. In terms of the elements that we have on this rover is basically we have a printed circuit board as part of the rover stack. We have a slip ring, which basically makes the electrical contact between the electrodes on the reel here and the electronics. And we have temperature sensors, one on the wheel and an infrared temperature sensor on the front part of the rover. The measurement accuracy is expected to be very good in this case because our electrode is basically pressed into the regolith by the weight of the rover. So we expect plus minus 2.5% over temperature. And the ice detection limit is expected to be about factor 10 better than on Prospect. On the one hand, because we have much bigger electrodes, and on the other hand, also because we go even further down in measurement frequency. The sensing depth is determined by the size of the electrode. We have 2 electrodes, one of them sensing to about down to 3 centimeters, and the second one, which is bigger, down to about 6 centimeters. And with that, I think I can wrap up. Basically, permittivity sensors are simple yet efficient sensors for lunar exploration. They can detect water ice at cryogenic temperatures and basically allow you to infer the density of materials, which can also aid other types of instrumentation. They can cover the concentration range of ice that is not only what is expected based on what we know today about the moon, but also they cover the range that is interesting for in situ resource utilization. So permittivity sensors are really an interesting tool for prospecting. The resource requirements are very modest. You can have configurations from only 1 electrode and only analog front end, and you can do that for a few tens of grams. If you reuse the digital back end of some other system, like rover electronics or another instrument. And of course, you can also go to much more complex systems using 4 electrodes and having a much bigger penetration range. We are working on 2 versions for flight now, one on Prospect and one on the Rashid rover. And I think with that, I can conclude. Thanks a lot for your attention. Again,
thank you very much, Roland. Time for a few questions before we head into our coffee break. Yes, please go ahead.
I'm just curious, how long does a typical measurement take to build up a good signal to noise?
Sorry, can you repeat?
How long does a typical measurement take?
It depends, of course, always. But the shortest measurements we plan to do on Prospect are 6 seconds. The longest ones on Prospect are probably 5 to 10 minutes in very rare cases. On the Rashid 3 sensor, we go to much lower frequencies. So we would also like to extend the measurements just to get more and more sensitive for water ice. There, the longest measurement is probably in the ballpark of 10 to 15 minutes.
Thank you.